All right, so we're going to start with a short introduction about what Markov state models are and how you would estimate them and what you can do with them, and basically set the scene for what is about to follow the next days. So on this slide, you can already see a small example of a Markov state model. You would have like a discrete trajectory here on the left-hand side, which jumps between two states, 1 and 0. This is what we would call a discrete trajectory, or in short, a D-trej. You will stumble across that word later multiple times. And you could describe such a discrete trajectory with a probability transition matrix, such as here below. I'll explain later more what this is, and such a discrete trajectory could also be realized in your continuous space, right? So for instance, you would have these two wedges, and each of the wedge would correspond to one of the states, discrete states, and then you could try to decipher based on a time series like this, or on a time series like this on the right-hand side, what was the ground truth. Right? This is a very simple example of a Markov state model. But why should we care, right? Usually, at least in molecular dynamics, you would have a system of interest. Then you have maybe experiments, or you have simulations, right? There's this little arrow here. Then you have a realization of that, or multiple realizations. From that, you can estimate a model. And this model then can be used to predict certain properties of interest. Yeah? And these properties of interest are usually coupled to a question that you have about the system. Yeah, vice versa, it's often useful to first think about a question that you want to ask to your system. Then you can run appropriate experiments and simulations, right, and go this way again. For example, right, we would have such a protein here. This is BPTI, and then you would have a very long simulation, which was run by D. Shaw. And you could build a Markov state model out of this. So this state model describes the different metastable states. We will come to the definition of metastable later. And the population of these, and how you would have transition between them. And from this kind of model, you can predict properties. Certain chemical properties, kinetic properties, thermodynamic properties. And these can be used to answer certain questions you have about a system. No. And Luis, who introduced himself just now, has kindly provided me with a small movie of CECR2, which is a protein to epigenetics, related to epigenetics. This is how it looks like. It has two states, or well, more than two states, but two major states, one of them being on the left-hand side in blue. And you can see on the lower left helix above it, there's this loop here, and it opens up, right? And this would be something that could be studied with a Markov state model. So let me just show you a movie of that. I hope the video isn't too chunky for you. So here it is in the first state, and it just wiggles around. And then eventually it makes a state transition into the yellow state and has opened this pocket. And this is also something that we would understand under metastability, right? It changes a little bit in the yellow state, but the changes aren't too large. So it mainly stays in one configuration and then eventually switches back. Yeah, here, switch back. And this, of course, allows us to project this massively high-dimensional thing, right? In the movie, you couldn't see it, but this is made up of atoms, and we would simulate these atoms individually and how they interact with one another. So it is very high-dimensional. We can basically project it down to, in the movie's case, two states which switch back and forth. Or here, in this case, which is again BPTI, we would have 4 states. Yeah. And then we can look at the transitions between them and transition rates between, for instance, this yellow state and a blue state. So all in all, we can simplify what we have simulated and then begin to understand what it actually does, right? So this plot here, right, we can also write a little bit differently in terms of a matrix, where we on the left-hand side have an initial state, on the right-hand side of a final state, and then we just write down the probability with which it would transition from the left-hand side, from this yellow state, to one of the other states. And you can see most of the probability mass is actually on the main diagonal of this matrix. So the protein likes to stay in the state it is currently in. There's a 69% probability that will not change state from one frame of simulation to the other. So we describe the dynamics of the system in terms of conditional probability distributions. So given we are in state yellow, what is the probability that we end up in state orange, for example? And so this is again to illustrate the concept of metastability. We have these four states, and they somehow live in Euclidean space, Rn. And these configurations are long-lived, and we want to find these long-lived configurations, and long-lived means metastable in this case. So it's not stable, but eventually it changes, but it stays there for a longer period of time. So we start in some state X, and then maybe we transition to purple, and then go to blue. And this would be a state transition with an intermediate purple to Y. This is something we could study with Markov state models. Now, what we deal with here are mostly molecular simulations, and molecular simulations are special in that they have certain properties we can make use of to make our lives easier. So molecular simulations in particular simulate a stochastic process, and we can look at a probability density of going from state X to Y, right? This is kind of this, in a discrete sense, one column of the matrix. And we look at a certain state X of T, right? And we say, okay, this is state X in our state space omega. And what is the probability given that we start here after a certain time tau to end up in an infinitesimal region around some point in state space Y. And this has to hold for every X and Y. And because we are simulating a stochastic process, this is actually well defined, and we can make sense of it. And of course, when we integrate over all the Y's that we're interested in, right, we can also look at sets. Right? What is the probability that given we start in state X, we end up in set A after a time tau? Okay. And then we have some more properties. So we also have ergodicity. That means that our state space is practically not disconnected. So we can reach every region of the state space eventually. That means if we have a lot of compute power, right, and we simulate for a very, very long time, we will see every possible state that this system can attain. This is what this means, basically. And then we also have reversibility. That means that the probability of jumping from X to Y or from Y to X is the same up to this mu, which is the stationary distribution, or the Boltzmann distribution here with the Hamiltonian. And in equilibrium, it's actually equal up to this reweighting factor. Yeah. So this is what we understand of reversibility. And so as you might have already guessed, if I go back to the very first slide, if I can, then we have this discrete trajectory here, which jumps between states 1 and 0. But if we look at this transition probability matrix, which gives us gives us conditional probabilities to jump from state 1 to 1 or from state 1 to 2, then this is actually a probability distribution, right? So we are not looking at a single point in state space, but we're rather evolving a distribution in time. And this is what this slide was meant to illustrate. So we have a single point in state space, but in fact, we rather consider an ensemble in state space, which gives us a density. And then we work with this density of states. And finally, there are some more assumptions about the fold dynamics. So first of all, the maybe most important and underlying assumption is that our process is Markovian. So if we look at the probability of getting a certain state x at time t plus tau, so at a current time plus some offset in a set A, given a time trajectory in the past, right? xt1 up to xtn, I guess here's an index missing, and these attain some states x. Yeah? Then this is actually only dependent on the previous step. This is Markovianity. So the jump probabilities really only depend on the step before. We don't need any further history, which is also why we can describe it as conditional jump probabilities. Yeah, we only need to consider one state, one initial state here in yellow. And then from this initial state, we know the distribution of future states. Yeah, we don't need any more time frames prior to that. And then we also have the Chapman-Kolmogorov property, which is a useful tool to validate whether we are actually dealing with Markovian data. And this says that if we look at the distribution at tau 1 plus tau 2, this is actually decomposable into the distribution at tau 1 with an intermediate y, and then tau 2 from the intermediate y to the set A. So basically this says that we have an additive property here with respect to the lag time tau. We can evaluate our system at xt plus 2 tau by taking xt and then propagating it twice. Right? This is basically what the Chapman-Kolmogorov property tells you. And then we have the further assumptions about the fold dynamics. So we have irreducibility. This is also akin with ergodicity. So here that means that we can reach all the states. So there's nothing disconnected. And there are ways to ensure this in practice. And we'll talk about them later today. But for now, it is just an assumption that we make about the fold dynamics. And with this assumption, we get a unique stationary distribution. The stationary distribution is the distribution that of states at, when the time goes to infinity. So you evolve a system and eventually you sample from the stationary distribution with respect to states. And then we have the ergodicity. That means that the states are not disconnected and we don't have cyclic dynamics. And this is quite the important property because it ensures that time and ensemble properties are equal. So if you think about simulating a system, then you would run a molecular dynamics simulation maybe, or some other kind of simulation. And in principle, it is enough to run one trajectory and run it for a very long time. And then you would see everything and you would know everything about the system you need in order to build such a model. But this is not very practical because we can not really parallelize it in time. But if we look at an ensemble average, we suddenly have a kind of a trivial way of parallelizing our efforts. Because this says we can also instead start a lot of simulations which are shorter and gain the same statistic or same statistical insight. Yeah. And then finally, we have reversibility. That means that at equilibrium, there is no probability flux really. So we have mass conservation. And this is something that can hold, but doesn't have to hold. Right? Usually it would hold in terms of molecular dynamic simulations. There are ways to enforce it, but it doesn't have to hold. There can also be sinks and sources in a Markov state model. Okay, so let's go back to this ensemble view of the dynamics, because this is really what we are going to work with. So usually you wouldn't have one very large trajectory, but a bunch of them, and because the other one is really impractical. So we have a kind of a density of states, yeah, at time tau, and then we can look at what happens to them if we propagate them at time t. Sorry, this is wrong. So at time t, we have an ensemble of states here, and then we propagate them with a propagator according to time tau, and then we can look at what is the ensemble of states then. And we can express this in terms of our probability densities. So the probability density of t plus tau is the probability density at t propagated with p tau, which is this integral. And the propagator really is the thing that we're interested in. The Markov state model in the end is our propagator, or an approximation of it. So let's look at a small example. Let's maybe first focus on the left-hand side, on the bottom half. So we have such an energy landscape, and you could imagine placing a particle in there. And this particle would be subject to overdamped Langevin dynamics, for example, and would just diffuse around in here and also be subject to this external potential landscape. Yeah, so we have the energy U of x, and then it will go in here and maybe diffuse around in here, and eventually it would maybe make a transition over here, and then maybe cross here, or vice versa, go back to A, right? And kind of one-to-one to this is also a probability distribution of states. So where we have an energy well, it is likely to find state, and on a barrier, it is unlikely. So such a trajectory might look like on the right-hand side, where you first stay for a while in state D on the right-hand side here, and then go to C, and then we fluctuate between D and C a little bit. And then eventually, in a rare jump event, we go to state B, and then fluctuate between B and A. So this is the example dynamics that we're going to look at for now. And if we look at the propagator for that, we can imagine that we have a vector of probabilities that describes the state of our system. Yeah, the state of our system would be, where is my particle? So you put a 1 there. You discretize this thing by setting up a vertical grid on this energy landscape, and then wherever your particle is, you set the grid value to 1, everything else is 0. And now if we look at the propagator with respect to tau equals 0, then we don't see anything, right? This would be a diagonal matrix because it doesn't propagate anything. This is the identity. Now, if we look at the propagator at a larger lag time, tau equals 200, then we have a different picture. So we would have a large density here around state A, and then eventually down here, if we go from left to right, you could imagine we would have a transition density between A and B, which is less than, inside the potential well. And if you go even to larger lag times, then this means that we don't even really see anymore the transitions between A and B, but only between AB and CD. Yeah? So this is really to show you that this propagator depends on the lag time that you choose. Yeah? So if the lag time is too short, like here, then we don't really see anything. Yeah? Even if tau equals 1, we wouldn't really see anything but noise. If the lag time is about right, then we could see the transitions between the states, A, B, C, D. And if the lag time is too large, we might miss something, right? We might miss that there are also states A and B, but we only see this combined state A, B. Okay, so why is this? This is because we are looking at processes. So if we have our propagator p tau, then this is a linear operator. That means we can decompose it into eigenvectors and eigenvalues, right? So then each of these eigenvalues corresponds to one jump process between AB or BC or BD, for instance. And these processes have timescales that belong to them. This is because of the because of the Chapman-Kolmogorov equality. Yeah, so we know that if we have such a lambda I, which is an eigenvalue, and we look at it at a multiple of the lag time tau, then we have this exponential relationship. And this means that if we increase the lag time tau here on the x-axis, the eigenvalues lambda, which are smaller than 1, will decay exponentially. Yeah? This is what this plot shows. And there's always going to be the eigenvalue 1. Yeah? This is a property of how p tau is structured. So p tau is something that we call a stochastic matrix, because every row forms a probability distribution. So we always have an eigenvalue 1, which describes the stationary process, right? That nothing changes basically. And then we have lambda 2, 3, 4, and further, which describe the other processes. And so then we have timescales assorted to them. And then there's this barrier, right? This dotted barrier that you can see here at 1 over E. This is when the lambda is exactly the lag time. So once we increase the lag time beyond, let's say 1000 here, we lose the process lambda 4. This is what you could see in this plot. Here, tau is 2200. We go back here, 2200 is somewhere here, maybe. And that means that the lag time that we propagate, the tau, is larger than the eigenvalue lambda 3 and also the eigenvalue lambda 4. So in this case, we couldn't resolve this process anymore. This is why we lost the faster transitions A, B, and CD. So this is one barrier, like this 1 over E. And you will see this later on many times. So I guess you'll become more familiar with it if it seems a bit foreign for now. And why we look at these timescales like this is because this TI doesn't depend on the K anymore, right? So what we can do is we can pick a lambda I and then look at how the TI behaves when we increase tau. Okay, so these processes, as I said, are described or belong to the lambda I, so these lambda I phi I actually, and we approximate our propagator, which is a linear operator, with these processes, right, with these lambda i's and phi i's. And what this gives us is actually a spectral decomposition. And then we can look at a gap in the spectrum. And because these eigenvalues are related to timescales, yeah, going back here, we have a timescale according to an eigenvalue. we can just throw away everything that is too fast, that we don't care about, because we care about meter stability. The assumption is that what is slow in the system is what is important in the system. And like this, we kind of approximate away all the noise that we don't care about. And well, everything that is faster than the lag time is not resolved really, and kind of disappears, because the propagator that we're learning doesn't see these processes anymore. Yeah, and this is an illustration of that. So if we look at the eigenfunctions of p tau, the phi's, then these correspond to the eigenvalues lambda I. So for lambda 1, we have the eigenvalue 1, because again we have a stochastic matrix. And this is the stationary process, so nothing changes. And then we have the phi 2, which is the slowest process, which would correspond to a jump over the BC barrier, right? The high barrier. Let me go back here. So this is the system again. We have a medium-high barrier between AB and a low barrier between CD and a high barrier between BC. So the phi 2 corresponds to a jump between BC. And you can actually see this in the eigenfunction also. The eigenfunction kind of gives you the shift of probability mass according to the jump, right? So you shift this probability mass here, this is negative, to the right-hand side. So there's a transition here between states B and C. And phi 3, which is the second, or well, maybe third slowest process, if you like, is a transition between AB, which is the medium-high barrier. And then we have phi 4, which is the CD barrier. And then if we look at the spectrum, right, at the eigenvalues, then we see that here we have a gap. Everything else is much faster and approaches 0 eventually. And this is where we would, in practice, make a cutoff, right? We say, okay, lambda 5, 6, 7, and so on and so forth don't interest us anymore, because the main dynamics is already captured by the first 4 eigenvalues, or the main kinetics, I should say. Okay, so how do we estimate such a Markov state model? Yeah? What are we facing? Yeah? So we are facing such a system, and because a Markov state model is something inherently discrete, we first have to make a discretization. And the discretization is a spatial one. Yeah? So we would discretize our state space, and here we choose a perfect discretization, right? We perfectly discretize by resolving each of the probability wells and then having a boundary kind of between the 2 states on the peak of the potential function. And this would give us a time series, right, of a particle which actually diffuses around an A, but we only see one value here. Yeah? So let's say A is 0, or red is 0, orange is 1, green is 2, and blue is 3. Then we would see something like 0, 0, 0, 0, and so on and so forth. And then suddenly we see 1, 1, 1, 1, 1. And then we see the same thing with 2, and then a short transition to 3, and back to 2, and so on and so forth. So this would be a state space discretization and giving us a discrete trajectory, which we can then use to estimate a Markov state model between these discretized states. Yeah, a more mathematical way to approach it would be saying that we subdivide our state space into disjoint sets and then have indicator functions on them. And the Markov state model describes states or state transitions between these indicator functions, or evaluations of indicator functions. Okay, so now we can count, right? We just count our state transitions. So we set up a count matrix, and we count for each tuple x1, x2, x2, x3, x3, x4, and so on and so forth. What is the state transition here? So most of the time we would, for instance, stay in A, right? We would see AA, and suddenly we see AB. And this would give us a 1 here, a +1 here. And then we don't see a BC, and we don't see a BD, right? So we have zeros here. And same thing for BA transitions, BB transitions, BC transitions, and so on. Okay, so this is something that we call a count matrix. And based on this count matrix, we can create a maximum likelihood estimator of the transition matrix, the P that we are actually interested in. So the likelihood of the transition matrix, so the probability that we have a time series x1 to xt under our model P, can be written down as just the product of the state transitions. Yeah. So given we have a probability matrix P and we see a state change x1, then we write here a P11. And then we multiply this up. And this expression is actually maximal if our model perfectly fits the data. We can rewrite this a little bit in terms of the transition matrix P, so Pij, the ijth element, to the power of the counts that we have, Cij. So P11 to the power of C11 times P12 to the power of C12, and so on and so forth. And if we maximize this for our parameters P, then we have the maximum likelihood estimator for our transition matrix. Yeah. And of course, we have some more constraints, right? We would like to have a probability distribution in each of the rows of our transition matrix. So we enforce that it is row-stochastic. And if we just enforce that, and because the counts are positive, or rather non-negative, I should say, we can show that the maximum likelihood estimator is really just the row normalization of our count matrix. Yeah? So for the non-reversible case, it is really that simple. Yeah? We just have to normalize, and then we get our transition matrix. If we want something reversible, then we can't do this analytically, but we can perform some fixed point iteration. And this is also implemented in deep time, and you will work with it later. Okay, and this gives us a transition matrix, but it doesn't really say anything about how robust our transition matrix is, right? So if we have a little change in our time series, how little would also be the change in the transition matrix? You would like that this is not very sensitive. And for this, we can do some Bayesian inference. So what we want is we want to sample transition matrices given statistics. Yeah. So we take the likelihood of before, we take the given the P, how likely is the, or how probable is it that the data x1 to xt was generated by P. And this is actually just based on the count matrix C. Yeah? So we look at the probability of C given P. And this is really just this product, this likelihood that we've seen before. Okay, and now if we do Bayesian inference, we use Bayes' theorem, and we can write it like this. So we have statistics about our data C, and we want to find the distribution given C over P and draw from it, right? So we're back at this expression of before, and then we have some prior information about the transition matrix itself, which, as it says here, can be used to enforce row stochasticity, reversibility, some stationary distribution, anything that you would have prior knowledge about, really. And then we can sample it with Markov chain Monte Carlo, and well, this is just an example. And based on the sampling, we can see how great the variance is of transition matrices, which are somehow eligible for producing the data that we've seen. Yeah. Okay, and then there are some alternatives. So if we run molecular simulations in, let's say, different ensembles, at different temperatures and so on and so forth, and there are reweighting techniques to combine them into one model, into an ensemble model. This is something that is included in PyEMMA, but we won't cover it in this workshop. And you could also look at augmented Markov models, which allow you to include experimental data into your estimation routine and then make the model reproduce this estimation data, right? You could think of this as kind of a stronger prior. This is also implemented in deep time and also in PyEMMA, and we're also not going to cover it in this workshop. But if you're interested in this, there is a tutorial available on the PyEMMA website, and I'll show you later. Okay, so how can we analyze our transition state model once we have it? First of all, we should note that the timescales that we obtain are always underestimated. Yeah, so here we have quite a significant difference between the timescales of what we estimated and the ground truth timescales. And this is something that we can make use of later on. Yeah, so not today, but tomorrow. We will introduce a variational principle. That means that we can score how well our model is, or how good our model is, based on how well these, for instance, timescales are approximated. And one thing to improve the model here is to increase the lag time. Yeah? If we increase the lag time, we may need fewer statistics or make the data more Markovian, and then our model works better and we get closer to the ground truth. This is because of the projection discretization error. So here we have the discretization that I showed before into the states A, B, C, D, but we could choose any other discretization, right? And then we have the eigenfunctions, psi 1 to 4. Yeah, the first one doesn't do anything. The second one describes a transition between states B and C, and then we have A, B, and C, D. And if we look at the relative error, right, in the non-dotted line, then this is quite good, right? This is quite good to the dotted one, which would be the perfect discretization, if you want. Now, if we take a bad project, so we kind of leave these transitions out, yeah, and we place it not directly on the tip, but kind of awkwardly around it, then we suddenly see that our timescales are much worse than the ground truth, right? And our relative error is also much larger. And this is also something that we can use for validation. Yeah, so if I go back here, we can see that the timescales eventually converge to a line. Yeah, so if we increase the lag time, we see these timescales become constants. And here, this doesn't really happen. Yeah? And especially this shaded region is when the processes have decayed. That means we're effectively losing the green and the blue process here, because before we can resolve them, before they became constant, which means that under our model, the data is more or less Markovian, these processes are faster than the lag time, and we can't really use that information anymore, or our model doesn't capture them anymore. So this is something that we can use for validation, and you'll also see this and do this later. And these problems are related to non-Markovianity, which is what I already said, and this is something you can validate with the timescales and also with the Chapman-Kolmogorov test. that I will introduce in a second. And often we also want to understand the full system, not just the observation. So that means even if we have data, right, this doesn't mean that the data describe the full system well. This could be just, let's say we observe the energy of a system. This doesn't really tell us that much about the configurations in it. And then there's a lot of freedom in the projections and discretizations that we choose. So here we have some freedom to make improvements to make it as Markovian as possible. And this is also something that can be evaluated rigorously, and that will be done later. So this is the Chapman-Kolmogorov test that I already mentioned. This goes back to the Chapman-Kolmogorov equality. So we know that if we, well, this is now a different notation, so this could be a P, right? T as a transition matrix, or P as a probability transition matrix. This means that if we take the state at tau, or the matrix under lag time tau, this is the same, or should be the same, as if when I take it to the power of k, as if I have it under lag time k times tau. And this difference we can evaluate, right? If we have an observed trajectory, and then we build a Markov state model out of it, and the lag time is too short, then it might be that the observed trajectory isn't really Markovian. So the Chapman-Kolmogorov equality is violated, and then we would see this red line. And this doesn't really agree with what we observe, right? The black one. And as we increase the lag time, the data becomes more and more Markovian, and we get closer to the black line. And this is also a validation technique. Okay, so in general, summing up, you would first project and discretize your data, and from that construct a transition matrix. And then from the transition matrix, you can look at the processes by making a spectral decomposition, eigenvalue decomposition, and looking at timescale gaps to find a reasonable cutoff. And based on that, we can also do a Chapman-Kolmogorov test to see whether our data was actually Markovian, or whether we need to increase lag time maybe. Okay, and what can we draw from this? We can draw from this, let's say, relaxation timescales, dominant processes. Dominant processes we've already seen, right, in accordance to eigenvalues. We can look at the stationary distribution, which is related to the thermodynamic behavior of the system. We can look at metastable sets, which will be covered this afternoon by Luis. We can look at correlation functions, so spectroscopic observables. We can look at mean first passage times between metastable sets, and we can look at path probabilities, which means how am I going to transition most likely from a set of states A to a set of states B, and what are the intermediaries? Okay, so summing up, with a Markov state model, we can derive a coarse-grained descriptions of the dynamics of the original system. And we parameterize it from simulation data, and well, then can compute properties of interest. And we have techniques to reduce the discretization and projection error, and also to validate that our model is, well, our model assumptions are not validated by looking, for example, at the Chapman-Kolmogorov test to see whether we have something Markovian. Okay, this is it for this talk. So do you have any questions about it?